We now return and summarize our major equations of motion, or the Navier-Stokes equations. We are considering Newtonian fluids, which, if you recall, is a linear stress-strain relationship between the viscous stress tensor and the strain tensor. And these are viewed as isotropic fluids, meaning that this will be retained and invariant with rotation, the statistics. And now we summarize the major equations. The first, of course, is the continuity equation. And the second is the momentum equation. The particular force density is a superposition of all the external forces in F and all the internal forces, such as the internal stress of the fluid at pressure and the viscous stress tensor. External forces might be something like gravity. So we have conservation of mass and momentum, which are traditionally and formally the Navier-Stokes equations. Often today, people say the Navier-Stokes equations, and they often are implying an energy equation and a gas law to close them. However, the original equations of Navier-Stokes were incompressible and decoupled. We have previously developed, through this course, the forces due to the internal pressure, or the internal stress of the fluid, which we write as negative nabla P, and the viscous forces, which would both be internal forces, of course, as mu of U and the second coefficient of viscosity of nabla divergence of U. We receive these boxed equations after inserting the forces in the momentum equation. The first equation, 97, is the material derivative of the mass density, rho, plus rho times the divergence of U. The second equation is the Navier-Stokes equation itself, the momentum equation, for momentum and velocity. And here's the pressure term, the viscous terms, and the body forces, respectively. Obviously, if you count the number of variables in the equations, we have rho, U, and P, and we'll need two additional equations to close it, which would be an ideal gas law at minimum, or some kind of gas law or equation of state. And the first law of thermodynamics is most typically used and is often called the energy equation. So we refer to these two major equations when talking about Navier-Stokes in their compressible form. Incompressible flow, of course, would have the D'Alembert equation, which would imply divergence of U is 0, which is the D'Alembert equation. If there's no viscosity in these equations, then we'll call it an ideal fluid, and mu and lambda, the first and second coefficients of viscosity, will be 0, and we'll automatically receive a set of equations we call the Euler equations. The trace of the particular equations is important. We can also find a total or mechanical pressure, which we'll write as P minus 2 mu plus 3 eta divergence of U. The bulk viscosity will be viewed as 2 mu plus 3 eta. This is really an assumption and not entirely correct, in my view, of George Gabriel Stokes. And he made the hypothesis, which holds, that lambda is mu plus eta. Often in compressible codes, this works really well, not to account explicitly for a bulk viscosity, but for high-speed flows and hypersonic flows, this might break down. As I mentioned before, in compressible flows, we might informally write that the density is a constant everywhere, which is a little bit overly strong assumption. And then we'll get the D'Alembert equation, divergence of U is 0, which is the continuity equation. And we'll have this nice simplified form of the Navier-Stokes or momentum equation in 99, which is just for velocity. And you can see that now density is decoupled.